Morning, my dear students. Last session, we have started talking about the portal method, which is uh, one of the methods in approximate analysis of laterally loaded frames. Okay. So, what we have seen in this portal method, let us just recall step by step that it is mainly based on the assumptions that will make the indeterminate structure into a determinate one with simple two assumptions made, which is proposed by the Albert Smith. So first one is common for both the methods. Either it may be a portal method or it can be cantilever method. So that first assumption is the point of contraflexure or inflection point occurs at the mid height of each column uh, of each member. Okay, so that is what is the first assumption. The inflection point occurs at midpoint of each member. That is the first assumption. Now the second one, which is very particular to this portal method, is the total horizontal shear at each story is divided between the columns of that story. That relation that you need to apply to the frame so that it makes your problem determinate is the horizontal shear in exterior column and the interior column are related. How they are related, let us see. So the interior column carries twice the shear of exterior column. This is the relation. Okay, so horizontal shear by the columns in a frame are being related. That is the main the assumption which differs from the methods, either it is cantilever or the portal method. So portal method is based on the assumption on column shears, that you should remember. So and later on we have applied the assumptions and we have seen how frames became determinate, how the indeterminacy value is becoming zero, which is nothing but the indeterminacy is zero means the frame became determinate. Okay, so this is what is seen in the last session. Now let us see how you solve a particular portal frame applied by horizontal loads, lateral loads, in the sense lateral loads, by this portal method. Let us see step by step procedure. So in this approximate method, this stepwise calculation is much important, and the flow of calculation is also important. Which quantity is to be calculated first, and then what to calculate next is very important. Means the order of priority of calculation is also matters in this portal method. Okay, so remember you have to start from the assumption. That will be your step one. Okay, so you first apply the assumptions So that the first assumption is on column shear. So we will calculate column shear first. That is your step one. So to calculate shear in each column, what you need to do. So for example, if this is the frame applied by some say 10 newtons, imagine. So what you need to do to find shear in this column 1, say C1, shear in column 2. As there is no interior column, you just need to have just shear in column 1 is equal to shear in column 2. That way you can simplify this problem, as because if there is an interior column present, then you can relate them interior column to exterior column. So as there is no interior column here, the shear in both the columns are same. That is your assumption. Okay. So what you need to how you calculate the column shear. Consider a section in the middle of each story and apply equilibrium equation called sum of horizontal forces equal to 0. So what you need to do, you have so many stories, doesn't matter. So the middle of the story, you pass a section. Okay. So take the upper part of the section, because if you come to lower part for equilibrium, you need to evaluate the support reactions. So that is not done. So to avoid that, we take the portion above the section. So what you need to do, you just have a free body diagram. So this is 10, right? So you have shear like this, you have shear like this. The directions that you have to fix based on this direction of 10. If it is towards right, we take it as towards left, likewise. So this is like V in column 1. This is like V in column 2. Okay, as both are same, you can just say VC1 is equal to VC2 is equal to VC. Okay, right? So what you do now, you need to apply this horizontal equilibrium onto this free body diagram. So what you need is say 10 is equal to VC1 plus VC2, nothing but VC1 or VC2. So it is 2 times VC. So shear in column from this VC is equal to 5 newtons, right? So likewise, we start calculating. Likewise, if you have number of stories, you have to take each story like that, then pass a horizontal section at the middle of the each story. Why middle? Is because you are assuming, your first assumption is that the point of contraflexure lies at that point. Okay, so that's why we choose that point for the section passage. Okay, right. So likewise, you have to evaluate all column shears in the entire frame given. Okay, that is step 1. Next, you have to calculate column end moments. As you know column shear value, you can calculate the end moments easily. Okay, so that's the point in why you need to take the step 2 as column end moments, because you see, I know this force to get moment at this end of the column. Say for example, I just draw it here. So this is the end of the column, and this is where I have shear force found, which is F5. Imagine total story height is 4 meters, and this is 2 meters, half of the story height. This is a point where end of the column. So 5 into 2 is the 10 Newton meter is the end moment value, and it is clockwise. This is one. Okay, so that's how you can easily find out. The other end also same way. So if this is a shear like this, and the bottom shear, and you know that the shear doesn't exist now with single arrow, and for equilibrium you need to have an arrow which is shear acting in the opposite direction. So this is 5. So the this end, if you want to calculate the moment, and that will be clockwise, same 5 into 2, 10. So both upper end and lower end of the column will have 10 Newton meters. So that's how you find end moments. So what you do here, multiply column shear with half of story height, which gives you column end moments. Okay, so just to remind you, the calculations are now just like now kindergarten calculations, just like multiplications, subtractions, divisions, additions, like this. So only thing what you need to do is you must make sure that the stepwise the calculation and sign conventions are followed with full clarity. Okay, and then only you feel this is easy. Okay, so this is the one where you can concentrate on for easy answering the question. Okay, it's very simple to answer to have maximum benefit. Okay, so let's proceed to the step 3. So you have calculated column end moments, let us say. So then what? So you have to calculate beam end moments. So once you know this, then you can know this one. Remember, as I told you, the procedure is is a regular flow, and where only when you know the previous quantity you can calculate the next quantity. See here, unless otherwise you don't know this 5, you can't calculate this as 10. That's simple it is. Okay, so first get column shear, then get column moment, then get beam end moment, likewise. So this will be done by the free body diagram of the joints. Okay, so this is a joint. Why it is a joint? You see there is a point of contraflexure here, there is another one here, there is another one. This is our first assumption. Okay, so now you can remove this part and draw a free body diagram. You see this one. Okay, so this is considering moment equilibrium of all joints. Beam end moments are estimated. So this is the joint. Just name it as some A, B. No, I'm just trying to explain you with a simple example. We will work out with much bigger examples. So this is joint B, where you have a column moment of 10 clockwise. Okay, so this one, this is 10. Now this is a beam, right? BC. Okay, so for sigma MB to be 0, because equilibrium should be there at the joint, so what you need to have here, an anti-clockwise 10. That's it. There is no other moment present anywhere there. So joint B, you have only one point load, no other loads. So you have 10 acting on the joint clockwise. For equilibrium, you should have an anti-clockwise 10. So that's That's much simple it is. So considering moment equilibrium of all joints, all such joints like joint B, joint C, likewise, you have, if it is a big structure, like you have a bigger one, if you take the frame, then you have much more joints and you will work out with all those joints. Okay, so this is step 3 calculation. So remember, you have started from the assumption. First you have applied the assumption. First assumption is anyhow common, and you have started with the second assumption, where second assumption will give you column shear values. Once you know column shear values, you are able to get column end moments. Once you get column end moments, then you are able to get beam end moments. Okay, then what next? So once you know beam end moment, you are able to get beam shear. Okay, so how you do it? Let us see. This is a beam where this is B. Okay, so you have an anti-clockwise moment of 10, right? Okay, let's say the span of the beam is total 8 meters. Let's say this is half of the beam, 4 meters, and we are now just taking the free body diagram of half of the part where till the point of contraflexion. This 4 meters is the half of the span of the beam. So now this is your shear. Okay, so you know the end moment as 10, and what is this force that will give you 10 here at this point? So to get moment at B 10, what force should be here? It is like simple. So V in BC, that means shear in beam, right? BC into 4 is equal to 10, right? Okay. It's just reverse to the earlier calculation. What? In case of column, you know shear, you are calculating end moment. In case of beam, it is just reverse. You know the end moment, you are calculating beam shear. So V BC is equal to 10 by 4. So it is 2.5. Okay. So that's how we get beam shear, right? So this fourth quantity calculation. Once you know beam shear, you are going to get column axial loads. Okay. So that's the last calculation. So how you get it? I'll tell you that you take free body diagram of the portion separated by uh, you know point of contraflexures or hinges. Point of contraflexure is nothing but zero moment point. Zero moment in the sense is a hinge, imaginary hinge you have. Okay, so you have forces like here there is a 2.5, right? Beam shear. Okay, you have a column here, so this is B, column AB. So what you have for free body diagram of that portion, what you need to have here, 2.5 downward force, then it will become sigma Fy 0. Okay, got my point? So 2.5 downward force, here it is 2.5 upward force. You know this already. So this force F, axial force F in AB is a column, will be calculated by just sigma Fy 0 to this free body diagram. Same here, it's written considering vertical equilibrium of free body diagrams formed by assumed hinges will give you column axial loads. So if you can just list out what you have calculated. So you have calculated column shear. That's first one. Then you have calculated column end moments. Moment in column. Then you have calculated beam end moments. Right. Once you know beam end moment, you have calculated beam shear. Once you know beam shear, you have calculated column axial loads. So 5 quantities must be calculated in this order, step by step. Okay. So you have 5 quantities, 2 in beam, remaining 3 in column. Okay, column will have 3 internal forces: shear, moment, and axial load. Beam will not have axial load. That's why you have only 2 quantities: bending moment, shear force, VB and MB. So 3 in column and 2 in beam. So total 5 quantities uh, in a step by step procedure, right? Likewise, you have to estimate throughout the structure. Okay. So this is the procedure, clear cut procedure for estimating internal forces in framed structures of indeterminate in nature, applied by lateral loads only. Okay. So we have started with the assumptions, 2 assumptions made by the portal method. You are following portal method. So portal method has got 2 assumptions to make the structure determinate. Okay. So first assumption is that each member has got the point of contraflexure or imaginary hinge at the middle of each member. Then the second assumption is that the internal column carries twice the shear that of the external column. This is the second assumption, and which is very particular to this particular portal method. Okay, and it is different for the cantilever method. So if you want to analyze a portal frame, then you have to start your calculation from the column shear, because it is the assumption. Okay, so where to start solving the problem? So start from column shear, then connecting quantity, column end moment you calculate just by simple multiplication. Then you calculate beam end moments, and then you calculate beam shear, then you calculate column axial load. So this is how simple the procedure. You see, there is no big equation anywhere. It's very simple calculation, just multiplication, division, addition, and subtraction. As I said, there is nothing more. But you have to be sure with your concept that the directions, sign conventions of forces and bending moments. Then ultimately you see the procedure is involving. Now you have applied sigma fx0. Okay, and you have applied sigma m0. Okay, and you have applied sigma fy0. Likewise, so this is all became determinate problem just with the 2 assumptions made by the Albert Smith. And we have even seen the earlier lecture how an indeterminate structure, by applying these two assumptions, is becoming determinate. Okay, so just have a clear idea about what to calculate first, what to calculate next, and then how to calculate it. Okay, anyhow, we will see much of the examples in further sessions. Okay, thank you so much.